When light comes to us, it doesn't come like a steady stream like water in a tap. Instead, it comes more like bottled water, little discrete packages, quanta, photons, little bundles of energy. The energy of a photon of light is given by hf. H is Planck's constant, and the value is 6.63 times 10 to the minus 34 joules second. You'll always be given that. And F is the frequency of the light. So we see very clearly that the energy of a photon of light is directly proportional to the frequency. Now, it's helpful to remember the little name Roy G. Biv, because that tells us the color of light in the rainbow. Red, orange, yellow, green, blue, indigo, violet. Red is on the one side of the spectrum, and the violet or purple is on the other. Red, the very important, low frequency, low energy, and the violet, high frequency, higher energy light. So E equals HF. Now, it's helpful to remember the velocity of a wave is lambda times, or wavelength times frequency. Well, here we're dealing with light, and the velocity then is c, and we can then solve for the frequency and rewrite that as c over lambda. So it's very helpful if we have the wavelength of a particular light, we can write E is equal to hc over lambda, another expression for the energy of the photon. Here's a question. What is the energy of a light photon with frequency 5 times 10 to the 16 hertz? Well, we take the formula, E equals h times f, and we merely plug everything in. H is 6.63 times 10 to the minus 34. Again, it's fine to memorize, but you will be given it. And that is joule dot second. And multiply by the frequency, 5 times 10 to the 16. Now, the frequency, of course, is vibrations or something, cycles per second. So we're dividing by seconds. And as you see, the seconds cancel. And we're left with the units joules. And when I put it through my calculator and rounded it off to two significant figures, or 3, I got 3.32 times 10 to the minus, 17, and that'll be joules. You can check me on that. Energy of a light photon. Let's try this one. What is the energy of a light photon with a wavelength? Well, we know to use this formula. E equals hc over lambda. And once again, we simply plug everything through and we find the energy of this light photon. So again, it's 6.63 times 10 to the minus 34. And that would be a joule second, of course, joule dot second. And the speed of light, 3 times 10 to the 8th meters per second. Well worth memorizing. 10 to the 8th meters per second. And we divide by 550 nanometers. Now, nano is 10 to the minus 9. So it's 550 times 10 to the minus 9 meters. Now, notice again, meters cancel. The seconds cancel. And I'm left with the energy of this light photon as 6.6, no, that's not true, 3.6 times 10 to the minus 19 joules. And that's how you find the energy of a light photon. But these energies are so tiny, there's something called the electron volt. Now, let me ask it like this. If we do work on an elementary charge, a proton, an electron, move it through a potential difference of 1 volt, how much work do we do, or how much energy would it gain? And you need to know then that the work is equal to Q times V. Now again, it's important that you have that memorized. Remember, the voltage is work per charge, so work is Q times V. So how much work would I do? And the answer is 1.6 times 10 to the minus 19 coulombs times 1 volt. And that would give me an answer in joules. Now that's so incredibly tiny. They choose to call that unit there 1 electron volt. Now it's so much more convenient to have a larger unit, an electron volt, and have it replace 1.6 times 10 to the minus 19. So you can convert electron volts to joules or joules to electron volts. Make sure you know all of this material very well.